Today, actually, I wanted to talk about concepts which are referred to as forces, but they are not really forces because they do not describe interaction of objects with the in the environment. In order to recognize, and actually I already used a phrase that sometimes in the past, however, I think that you have forgotten this phrase. I wanted to talk about, well, they are referred to as pseudo-forces, which result from non-inertiality of a reference frame. They are introduced just to save, well, relationship between acceleration and a force so that it looks exactly the same way as Newton's second law. However, we have to recognize that these pseudo-forces do not recognize interactions. We just add those artificial products of mass and acceleration to make up, to complete the equation. Well, in order to comprehend that, we have to think about non-inertial reference frame. So let's say that this black reference frame over here is an inertial reference frame, and in this reference frame, somebody at the origin of that blue reference frame moves in that inertial reference frame and spins on top of it. Yeah, so for example, if I choose x-axis over here, y-axis over here, and z-axis over here, let's assume that you constitute inertial reference frame, and if I start to do something like that and observe universe this way, I was looking now from a non-inertial reference frame. You can imagine, in this one, probably it was very difficult to imagine how let's say, Josh, how Josh was moving. But if I do something easy, or let's say that I move like that, what Josh is doing, how do I see Josh? He's moving back and forth like that for me. Now, how about if I turn like that, what Josh is doing? He is orbiting around me. Yeah, I see him circling me. Right? Okay. Yeah, so it is that the origin here moves, and it does not move like in Galilean transformation at constant velocity. That velocity can change. So this position is an arbitrary function of time in general. This angular velocity is also rotating. Well, so if this reference frame rotates, well, think about my vectors I, j, and k. What do they do in your reference frame? So I will call them I prime, consistently with the drawing, I prime, j prime, and k prime. So this is the direction of I prime for me. This is the direction of j prime and k prime. And what do they do? They rotate too. Yeah, so my base vectors are not constant in your reference frame. In your reference frame, your I, j, and k are constant. So axes x, 1, and z are in your reference frame. X prime, y prime, and z prime are in my reference frame. Now, if that reference rotates, well, then vectors I, j, and k rotate. So recall from previous lecture what happens with the rate at which a vector changes. Well, we saw that when it was rotating and we knew angular velocity, the derivative of position vector was the same as multiplying the vector by angular velocity. Do you recall that? I mean, I wrote this expression that velocity, it was for a particle, but the particle was at the end of a of a position vector. So we found that velocity was equal to angular velocity multiplied by position vector for a rotating vector r. Well, now we have that vectors I, j, and k are rotating. So it means that, well, and velocity really is rate of change of the position vector. So if I think now about vectors I, j, and k, I can write down that each of them, rate at which it changes, is equal to angular velocity times that vector. So rate at which vector I changes is product of angular velocity of the reference frame multiplied by vector I. Rate at which vector j changes is angular velocity multiplied by vector j. And rate at which vector k changes is angular velocity multiplied by vector k. All right, let's now think about motion or description of motion of a particle seen from both reference frames. I can recognize now that the arrows representing them, yes, so arrow position vector in unprimed reference frame is that green arrow. In the rotating reference frame is that red arrow. And here we have relative position of the origin. So from this triangle, I can recognize that this vector r is equal to capital R plus this red one. Now, so in other words, if you think about relating a description of Josh's motion in my reference frame and in your reference frame, you are the black one, you will have to take my position with respect to you and then how I see Josh. Now, I assign scalar components of his position using variable base vectors. So I wrote actually this vector r prime as a linear combination of my base vectors, not yours, mine, which are functions of time in your reference frame. Do you understand that? Are you following me? Okay. So how about if I try now to relate velocities? Now, what I'm going to do is I'm going actually to go further to acceleration, because acceleration is the one which is linked to interaction through Newton's second law. Because mass times acceleration is equal to the net force. So my goal is now to relate acceleration, which I observe, with the interactions which I can identify. And I identify the same interactions as you do. However, my description of motion is different. So in order to relate velocities, what do I have to do? How from position I get to velocity? Calculate derivative. Now, calculating this derivative is pretty complicated, but I want you to comprehend it. Yeah. So now, consult with each other where I got this term from. Can you help me? It's derivative of relative position of the origins, right? Now, over here I have sum of three functions. And each of those functions on top of it is a product. So derivative of a sum of functions is equal to the sum of derivatives, which means that I will have derivative of this product plus derivative of this product plus derivative of this product. Now, in order to calculate the derivative of this product, here I have product of two functions. What do I have to use? The product rule, which means derivative of the first function multiplied by the second function plus the first function multiplied by the derivative of the second function. All right, so where did I get this term from? It's derivative of this function multiplied by this vector, by the second function. Now I have this function multiplied by derivative of the other function. I put it over here. Yeah, so these two terms come from calculating the derivative of this product. Now, when I calculate the derivative of this product, I have derivative of the first function multiplied by the second function plus the first function multiplied by the derivative of the second function. And for the third one, I have derivative of the first function multiplied by the second function plus derivative plus the first function multiplied by the derivative of the second function. All right. Now, what's that? Rate of change of position of this observer with respect to this one. Why? Why is, somebody says that it's 0. Is it? Think what is R. Yeah, so how about if you think about yourself and me? Yeah, now I'm doing something. What happens with that R? Changes, right? So is rate at which it is changing 0? No. And actually, what is the physical sense of the derivative of R for me and you? Not the distance. Let's say in English what's R. Show me R. It's my position vector with respect to you, right? So if I take derivative of position with respect to time, what am I going to get? My velocity, correct. How about if we go with, right? So I wrote here, it's velocity, this is velocity of the origin of that non-inertial reference frame. Well, now let's take a look over here. This is derivative which I calculate. All of this is which I calculate in my reference frame, right? Now I take derivative of x component of position of the particle which I'm observing. So Josh was the particle for me and for you as well. So if I calculate derivative of x component of his position, what am I going to get? Not velocity, but you're on the right track. X component of velocity. Right, so I wrote it. Here I have x component of velocity which I observe multiplied by vector I. So actually this product gives me what? What vector? Yeah, because this v prime x is the derivative of x scalar component of position, which means that this is scalar component of velocity. If I multiply by vector I will get what? Vector component of velocity, correct. So this first term is x vector component of velocity. How about that? Y component of velocity, y vector component of velocity, and this one is z component of velocity. How about that linear combination? What's that then? The velocity. What velocity? Velocity vector, but of what? Where? Of Josh, observed by whom? You. By me, correct. Yes, so over here, it is velocity of me, observed by you. Now here I have velocity of Josh, observed by me. All right, now let's go to these. Here I have to calculate derivative of vector I. What am I going to get? How did I get that? Well, I just spoke about it over here. Right? Derivative of I vector with respect to time is angular velocity of the reference frame multiplied by vector I. Now this is I prime, right? So this is my vector. Yeah, your vectors I, j, and k in your reference frame, they are fixed. My are moving in your reference frame. All right, so rate of change at which vector I prime varies is angular velocity of what? Of my reference frame. Yeah, so at what rate I am spinning. Where? Because I am spinning in my reference frame. I am spinning in your reference frame, right? How do I spin in my reference frame? I don't spin in my reference. I spin with your reference in your reference frame. Okay. Now, how did I make this step? Yes, so now instead of having this scalar component of Josh's position in front of this product, I put it next to my vector I. It's not distributive. It's associative. Yeah, for associative property. Remember that if I multiply a vector product by a number, I can multiply any of the factors. I can put this number in front of any of the factors. Now I am going to use actually now distributive law as well, because each of those vectors now is multiplied by vector omega. I can pull out omega and have the sum x prime I prime plus y prime j prime plus z prime k prime. What is that linear combination? This linear combination of base vector. How about that? Why don't you recall what is x prime? X component of Josh's position in my reference frame. I multiply it now by my x base vector. Now here is y scalar component of Josh's position in my reference frame, and multiply by vector j, which this gives me y vector component of Josh's position. And here I have z scalar component of Josh's position, and I'll multiply it by vector k. So this is z vector component of Josh's position in my reference frame. Right, so how about if I write it that way? And now I can recognize what is this linear combination. What is it?
Linear combination of base vector.
Yeah. Which gives me what? His position. Where? In my reference frame. Correct. Right. So if I write it down now in an abbreviated form, velocity in your reference frame is equal to my velocity in your reference frame plus Josh's velocity in my reference frame multiplied by my angular velocity in your reference frame and Josh's position in my reference frame. Now it would actually now if I think about Galilean transformation, what will be different in Galilean transformation? Some of those quantities will have a particular values. In Galilean transformation, I cannot rotate. My angular velocity is a zero vector, which means that this term disappears. And on top of it, position is a linear function of time, not an arbitrary function of time. So this will be just my velocity in your reference frame, and we would have Galilean transformation. All right. Now, how from velocity to relate accelerations? Yeah, because now we related velocities. This is velocity which you observe. This is velocity which I observe. Now, if I want to relate accelerations, what do I have to do? Take derivative of velocity. So we have to take now derivative of this function. Oh, now this will be a much longer task because we have more terms. So over here, I again wrote explicitly what is velocity. So I came step back. Yes, I wrote velocity as a linear combination of base vectors in my reference frame. And I also wrote position as a linear combination of base vectors. Well, this time, here I have sum of products, and here I have sum of products. So I see that I will have even more terms than before. Well, but it's not that bad. Okay, so derivative of the first one gives me this term. Now I calculate derivative of this expression. So I have derivative of first function multiplied by the second function plus first function multiplied by derivative of the second function. And recall that derivative of I was omega times I. Now, derivative of the first function times the second function plus the first function multiplied by derivative of the second function. Note over here, by the way, that instead of a component of velocity, I wrote rate of change in position. All right, so these terms, these 6 terms result from differentiation of the sum. Let's now take a look at that expression. Now here we have 2 products. One product is here, and then each of those is a product. In principle, angular velocity at which I rotate doesn't have to be a constant. I can vary it. So in principle, it is a function of time as well. All right, so I'll start. Derivative of the first function multiplied by the second function plus the first function multiplied by derivative of the second function. Now the second function is again sum of products. We have already differentiated that one when we calculated velocity. So it gives me derivative of the first function multiplied by the second function plus the first function multiplied by the derivative of the second function. So I took care of differentiation of this term. Now from that one will be derivative of the first function multiplied by the second function plus first function times derivative of the second function. And the same thing for the third one. Now let's fold it so that we'll neatly write it down. And this is what we are going to get. Let's recognize that. Yeah, so here, well, I copied the left-hand side over here. Now, this A, it's this derivative, which means that if we talk about you and me, what is that capital A? It's rate of change in velocity of what? Me, correct. So this A is my acceleration in your reference frame. Now, what's this A prime over here? And let's think about X, Y, and Z in my, X prime, Y prime, Z prime are Josh's position, right? So A prime would be Josh's acceleration, where? In my reference frame, correct. Now, with this one, where did it come from? It came from 2 terms. Over here, look at that. I can put this number wherever I want. So I will put it next to I, and this number next to J, and this number next to K, and pull out angular velocity. So I will have angular velocity, and now this is X component of Josh's velocity in my reference frame. This product will be Y vector component of Josh's velocity in my reference frame, and Z component of Josh's velocity in my reference frame. So I have to multiply angular velocity of my reference frame in your reference frame by Josh's velocity. So I will have omega times V prime. But this is just one. There is one more place, this one over here. So this term and this term appears twice. Therefore, I have to put this number 2. Okay, now the next one is from here. I have rate of change of my angular velocity in your reference frame. So we call it angular acceleration. So I mark here my angular acceleration, which you observe. multiply, and this linear combination gives me what? Josh's position in my reference frame. So I have to multiply my acceleration, which you observe, by position which I observe. And the last term over here, I can, well, I have omega times, and if I can also pull out that omega over here, and I will, this sum is really my angular velocity times Josh's position, the way I observe Josh's position. And here is another omega, so I have omega times r prime. All right, so now we see how accelerations are related. Now, if it is, if we talk about Galilean transformation, what will happen with each of those terms over here? Let's start with this one. What happens with this one? This one will go away, right? Because in Galilean transformation, I would have to move with constant velocity with respect to u. All right, how about this term? Does it go away or not? No. It is how I see Josh, right? Now, how about this one? This goes away because I'm not supposed to rotate, right? So my angular velocity is 0. So actually, this one goes away and this one goes away as well, right? What do you say? This one? No, this is my angular velocity which you see. So how I spin according to you. Yeah, whatever is with prime is in my reference frame. Whatever is without prime is in your reference frame. All right, how about that one? What happens with this term? Does it go away or not? Why not?
Is that my acceleration?
No, it is my angular acceleration in your reference frame. At what rate I'm changing my angular velocity? I'm not changing here because it was 0. My angular velocity was 0, so I'm not changing it at all. I keep it all the time at 0. So this term also disappears. Well, which means that practically everything is gone on the right-hand side. This is gone, this is gone, this is gone, and this is gone. Right? So what is left? A prime, correct. We will get that Josh's acceleration in your reference frame is the same as Josh's acceleration in my reference frame. That's good. Yes. DJ, right? JD. JD is happy, and I'm happy, and you should be happy too. Yeah, because this is what we saw for relationship between accelerations in both reference frames. Actually, this equation that accelerations are equal make my reference frame inertial as well. Any inertial reference frame related, any reference frame related to an inertial reference frame through Galilean transformation is also inertial. However, if I'm spinning and accelerating, I'm not related by Galilean transformation, and my reference frame is not inertial anymore. Let's now take a look at Newton's second law. What is the product of mass and acceleration, which I would assign to Josh? Yes, so Josh's mass multiplied by acceleration of Josh, which I observe. In other words, I'm curious about ma prime, because ma actually is equal. We know what it is equal to. Recall that your reference frame is inertial. So if I multiply mass by acceleration of Josh in your reference frame, what am I supposed to be? This is supposed to be equal to what? To which force? The net force. correct. Newton's second law says that in an inertial reference frame, product of mass and acceleration is supposed to be the net force. Now, in my reference frame, it's not. Let's see what it is equal to. Well, so I will actually move all the terms to the other side, right? Now, product and multiply by Josh's mass. So I will have mass times Josh's acceleration is equal to mass and Josh's acceleration in your reference frame, which gives the net force. Now I will have mass, I mean this one on the other side will have minus. Right? So I have to put Josh's mass times my acceleration. I have to subtract it from the net force. I have to subtract Josh's mass multiplied by this term, and Josh's mass by this term, and Josh's mass by this term. Yeah, if I were Galilean, constituted a Galilean, I mean, if I were related to your reference frame through a Galilean transformation, then all these terms would go to 0, and in my reference frame, also mass times acceleration would be equal to the net force. But now it is not only net force, but I have to add those terms. And those terms are referred to as inertial forces. And I put them in quotes because I cannot identify the source. There is no object which relates that force. They are a consequence of transformation of acceleration. Know that all of those forces are proportional to the mass. Also, we refer to them as pseudo forces. And actually, they even have names. The first one is referred to as just inertial force. And how about if we try now to think, I mean, to see it? Yes, so let's say that I will choose x to be in this direction. Oh, how about consistently with you? X in this direction, y in this direction, and z is in this direction. And now, from I can look at Josh and identify forces exerted on him, on everybody of you. What forces I would recognize? Real forces. Gravitational force exerted by the Earth and the normal force, one exerted by the chair and one exerted by the floor. They cancel each other out and they are 0, right? So they add up to 0. So I can recognize that the net force exerted on Josh is 0. Now how about if I accelerate? I accelerated in this direction. So this capital A was not 0. Well, I have now to multiply Josh's mass by my acceleration in this direction, and this will give me that inertial pseudo force. You can recognize that all remaining forces are 0, so there is only one force exerted on him. His mass times my acceleration. So how do I observe Josh's acceleration? Well, I have Josh's mass times acceleration, which I observe, is opposite to Josh's mass multiplied by acceleration, which you see that I accelerate. Well, I was accelerating that way, right? So I can recognize that if I divide it now by m, I will have Josh's acceleration. So I see that, I mean, indeed, Josh's acceleration in my reference frame. Which way did he accelerate in my reference frame? That way. I accelerated in your reference frame that way. His acceleration in my reference frame is opposite to what you see that I accelerate. Do you see that? All right. Now, the second term, which is responsible for hurricanes on Earth, is referred to as Coriolis force. And Well, Coriolis force depends on the velocity. So over here, I would have to multiply 2 times mass of Josh times the way I rotate. So for example, if I rotate that way, what would be my angular velocity? Up, right? Now, I have to multiply it by Josh's velocity. Yeah? So for example, if I look like that, how do I see Josh's velocity? He is moving that way, right? So angular velocity is up. His velocity is this way. If I multiply these two vectors, I will get a vector away from me. And then I have to take minus. So Coriolis force exerted on Josh is toward me when I spin like that. And it has value 2 times omega times v prime. If I rotate at constant rate, this term, which is referred as Euler force, is 0. Now, the last one is referred to as centrifugal force. And let's see which way centrifugal is exerted on Josh when I spin, right? So, first, Josh, angular velocity is in this direction. Josh's position with respect to me is that way. So vector product of omega and r prime is going to be that way. Now I have to multiply again omega by this velocity, which will give me vector that way. And now I have to take minus of that. So centrifugal force exerted on Josh is in the other direction. Now, if you compare, there were 2 non-zero forces exerted on Josh, Coriolis force and centrifugal force. Now, if you think about magnitudes of them, you recognize actually that velocity, I can write Josh's velocity also in terms of omega. It will be omega times r prime. So Coriolis force will be twice in magnitude to centrifugal force in this situation. So the resultant sum of forces and pseudo forces will be which way? Yeah, that one was 0 because all forces are balanced. I was spinning, not accelerating, so this one is 0. Coriolis force was toward me and twice as big as centrifugal in magnitude. The Euler force was 0. Centrifugal force was away. So resultant force is toward me, right? Toward me. Does it make sense now? Now, imagine how he is moving. Yes, so I can result that the sum of net force and pseudo forces is toward me, which means that Josh is supposed to do what? Not fly toward me, accelerate toward me. Correct. He is supposed to accelerate toward me. Now, his velocity in this is in this direction. Acceleration is perpendicular. So how is he moving? He's changing the direction of velocity. Is he? How do I see him? He's orbiting me, right? So he's moving like that around me. He's indeed accelerating toward me as a result of the pseudo force. All right, now I want you to think about situations. So put the cup with coffee on the dashboard and accelerate, turn the car and look at that cup of coffee and think about pseudo forces. Identify pseudo forces exerted on it, because the net force will be 0. It's pseudo forces which will move the cup. All right.